Okay, welcome everyone. Thank you all for coming. So we're very happy to have Alberto Bietti, who is going to tell us all about convolutional representation, kernel methods, and all of that good stuff.
Cool. Okay, thanks, Seb. Happy to be here. And yeah, so I'll be talking about a lot of work that I've done sort of through my PhD with my advisor, and at the end, also some recent work with other people. And basically, we've tried to study various properties of convolutional representations. So it's going to be based on some kernels as well, so as a formalism, but essentially we just try to study what we can have just through the architecture that one might use in deep learning. So, okay, so these are just general properties that make it such that deep learning have been successful in images. So when you have signals, typically, you can expect that there's various properties that you can exploit in your models. So, and CNNs have been widely successful recently in exploiting these properties. But these properties haven't really been well studied in theory. But some of these are typically the multiscale and compositional aspects. So this means that you can typically look at neighborhoods of images, for instance, at different scales. There's some local stationarity, which means that basically you typically look at the signal in local neighborhoods, but you use sort of the same operations throughout the signal. You have some invariance that people hope to achieve, for instance, translation invariance. And of course, these models have been state-of-the-art in like image recognition problems, as well as speech and other areas where typically the data are just natural signals. So some of the questions that we ask are regarding theoretical properties of these representations. So the first is, so we sort of know that there's some invariance to translations, but can we go beyond translation and study deformations? So I'll tell you more about that later, but essentially it's a richer group of transformations. Then how do we, if we care about translations, how can we go beyond translations, maybe to look at rotations or scalings? The other thing is, if we want invariance, typically there's a trade-off with how much information you can preserve about the signal. So how do we deal with preserving information throughout the network? And finally, how does all of this relate to model complexity? So when you're trying to learn some functions, ideally you would want a measure of complexity to have some like learning guarantees. So a lot of this is going to be based on kernels. And the reason is because it's a nice way to study nonlinear functions, nonlinear representations. And so just a little reminder, because I guess until like a few months ago, people didn't really care about kernels that much anymore. But so here, basically, if you look at some data X here, you try to map it to some like Hilbert space H through this kernel mapping. So you just map data to a nonlinear high-dimensional space. And then these nonlinear functions can become sort of linear in that space. So we take functions that are essentially of this form in a linear representation. This typically involves learning with a kernel, but there's ways to approximate it, and just generally it's a nice way to study nonlinear functions. So here, basically, we're going to construct some kernels based on previous work of my advisor that essentially this mapping phi and the kernel itself will have embedded into it somehow the architecture of the network. So this will be, there's various ways in which this applies to real networks. So just briefly here, but we will see them later. So one way is just using the network by itself, which actually when you do some nice approximations, it does look like something like a CNN. The other way is potentially we will study the kernel space, so this H space, the RKHS, which will actually contain practical functions, and then we can see how to control complexity using those measures. And finally, I won't talk about this too much, but there's also some relationship to optimization through what's called neural tangent kernels, but I'll leave that for the end. So, okay, again, on why we might care about this. So the point here is really to study sort of the architecture, somehow the inductive bias of the architecture, and separate that from the model itself. So here, phi is just something that doesn't depend on the data. So we can just study it sort of by itself. This will allow us to study both stability, invariance properties, and this preservation of the signal. So signal here is X, but yeah. And then the model is when you actually try to learn, then you will deal with this F, and this affects also generalization guarantees. So it's kind of a nice measure of complexity, and it also incorporates stability because when you're you can control this using Cauchy-Schwarz. You can basically, when the phi kernel mapping is stable, then this directly applies to the learned models. And this also tells you that there's some links potentially. If phi is a stable representation, then this will directly control how stable the predictions of some model f will be. And because small norm functions typically are easier to learn, then this also tells you something about learning complexity. So the other perspective will be more of a signal processing point of view. So here we will basically consider x, the data x will be signals. So actually define on continuous domains, because it will make it much easier to study these kinds of properties. And then we will look at this deformation property, this deformation group. So essentially we will consider these transform signals here, where x of u is the location, but we will consider essentially something more richer than translations. So here each point u will be able to be translated by a different amount, and we can hope to control how far the representation will be between these two different images. So so here, for instance, for MNIST, if you look at these digits, you can kind of expect that these two will be a small deformation from each other, whereas going from a 4 to a 5 will involve like a much larger deformation. So it's a useful inductive bias sort of when you're learning with images. And there is a nice formalism for this that's been introduced in the context of the scattering transform by Stéphane Mallat. So this was basically a non-learned, just handcrafted representation using wavelets. And essentially you can control, there will typically be two terms. One controls how large the deformations are, and the other, this one is just like the global translation invariance. And yes, again, this is just as a motivating question. So I'll start with just constructing these deep convolutional representations. So essentially this kernel that we will be studying. And so again, x will be a continuous signal. So here, omega is just RD, which is, so D is not the dimension, it's just how many dimensions your signal is. So for images it's 2, for audio it might be 1. And each point here will be sort of in R3. You can think of RGB pixels, so just like 3 dimensions per point. And then we'll basically construct layers in this using some operators at each layer. You can think that if you have some feature map, which originally will just be the original signal, what we do is we typically extract some patches near each point. Then we will apply some nonlinearity, which here will be some kind of kernel mapping. And then finally we will apply some linear pooling. So I'll go more in detail through all of these. So here's the general picture. If you're familiar with CNNs, you can think of this patch extraction as sort of the size. This patch will be essentially the size of your filters that you apply at each layer. Then you apply some nonlinearity, then you do some linear pooling. So linear pooling here because it's simpler in our context, but people in practice might use something different.
The nonlinearity is what?
Okay, I'll get to it. Yes. Okay, so the patch extraction, essentially, we just take this operator, which in point U will actually have sort of a vector of all the neighboring points. So just this little box around each point U. So this is just, it extracts a vector from each location. And this, if you use appropriate norms, so we use kind of L2 norms on the signals. And if you normalize it appropriately, then this just preserves as the norm. So the next one is this nonlinear thing. So when we take a patch, we have essentially a vector, and then we map it through this function phi k here. And we just hope some nice properties. We will require some properties to get stability. And in particular, what we will have is something like this. So this will be non-expansive. So phi, you can think of it in the context of kernels. This will just be a kernel mapping. So I'll show later what kind of kernels we consider. But essentially, we will assume these two non-expansivity properties.
So phi k doesn't output a scalar.
It outputs some element of RKHS, or some Hilbert space,
Oh. Okay.
So here you take a patch. So if you want to take the analogy to CNNs with some filters, this phi would just do like some linear mapping plus a ReLU pointwise. Okay. So it could be like a vector at the end, yes.
I see, okay.
But here we actually...
We think about it as outputting a point in the...
So in this kernel context, yes. So we take the patch, we map it through some kernel into some subsequent RKHS.
Okay.
And all that we'll require is just this non-expansivity. And then potentially for preserving information, we'll have some other properties that we'll require, but yeah. And a lot of the kernels actually will have these properties. So if you have this point y's at each point u, then you also have this sort of full operator on the L2 map, on the L2 feature map, which will have the same properties. Yeah, so you can also have something that's Lipschitz rather than non-expansive, and you will pay some factor later. But okay, so where do these come from in the context of kernels? Basically, we study these kernels that are nicely suited for hierarchical kernels. So these are dot product kernels. So essentially here, so why dot product kernels? Because typically here the patches themselves might be from some previous RKHS. And so we want to be able to take like inner products. So these are natural kernels to study in this context. And so the phi here is basically the kernel mapping. So you have this inner product that's equal to the kernel. And this will be defined where Z here is just a patch in one of the feature maps. And okay, so typically here we take kernels of this form. So just like polynomial expansion with positive coefficients. And we have some assumptions on the value at 1. And okay, so for these kinds of kernels, essentially you preserve the norm and then you're non-expansive. So it has the properties that we need. And for some examples, so if you take just a Gaussian kernel on the sphere and you take this this kind of kappa, then it has the properties that we need. Same for this other inverse polynomial thing. And the same is true also if you consider, so there's some kernels that have been studied that have correspondences to activations. So if you take ReLUs, then you get some kind of arccosine kernel that will have the properties that we need. Yeah. Okay. So in practice, when you get this, these kind of phi k's are not really tractable, especially if you're in a convolutional setting. So there's ways to approximate it that have been studied. So this is both approximating the full kernel method because you don't want to compute the full sort of n by n matrix, but also because even a single evaluation here might be complex due to this complicated convolutional structure. So yes, this is just some previous work of my advisor where he studies ways to approximate it using essentially a Nystrom type method, where instead of considering this phi, you project it on a finite dimensional subspace of the RKHS, and this leads to a tractable representation that's just finite dimensional. That's just a picture here, but it's a complex picture, so I'll skip it. Okay, and finally pooling will just be linear here. So essentially we have this feature map where we've mapped everything to some RKHS, and then we do some linear convolutions, just Gaussian convolutions, so kind of a simplified pooling layer. And
so the pooling is just is a Gaussian convolution?
Yes.
That's what you're saying?
Yes. Okay. So you could take something different, like average pooling, which is kind of a window. Here we take Gaussian for simplicity, but the theory should extend to something that's sort of smooth approximation of average pooling. But so this will have some scale, and here, so we just take essentially the scaled version of a normal Gaussian, which gives nice non-expansivity properties. Okay, just recap. So patch, PK, MK, and AK are these three operators that we consider. And essentially, we will construct this hierarchically.
The hierarchical, yes. The hierarchical aspect is that phi k is going to be applied recursively, or what's going to happen?
Yes. So all these operators, we can stack them.
Or you're going to all stack them?
Yes. So when you consider patches, you can consider patches on a different space. It will just take a vector of elements from some space H, and so you just create recursively these Hilbert spaces. Yes. Okay. So. Yeah, so one assumption that we'll need is that the original signal typically is discrete in practice. So since everything is continuous here, how do we make this, how do we reflect this? It's just basically we do some anti-aliasing. So typically when you take a picture with your camera, there is some kind of, you're cutting off some really high frequencies automatically. And so here we'll make basically an assumption of this form where there is some pooling already that is happening at the first layer. So X0 will be essentially your signal which we have in the discrete representation, and X will be sort of the natural signal that might appear in nature. And then we just stack all these operators for like n layers. And because everything is continuous, we won't really do downsampling here. So you can consider that the patches, instead of like taking patches and downsampling, we'll just get bigger and bigger areas at each layer. So typically exponentially. So both the patch sizes and the scales of pooling layers. And at the end, once we have this phi, you can just do some linear layer at the top. This will give you a kernel at the end. Okay. All right. Okay. So a couple slides about the discrete representation. So since in practice we have discrete signals and we do some kind of downsampling, so how do we convert this continuous representation to discrete? So typically after you do pooling here, you want to downsample your discrete signal by some factor, which is controlled by essentially the resolution of pooling. And then essentially for appropriate kernels, we can show that the representation can actually be reconstructed from the next layer. So you can go back one layer without losing information. So this is as long as you subsample by something smaller than the patch size. So essentially the patch size, the whole patch, when it's mapped to some next layer, it will have information about the entire patch. So even if you skip, if it's like a 2x2 patch, then you can take every other pixel and it will have enough information in the kernel representation to represent the previous layer. Yes, and this is when the kernels have enough information, you can do this. This is just a picture, but yeah, so it does involve some sort of deconvolution, and it's not a practical method at all. It's just to show that essentially the information is there. So maybe if you want to like memorize your training data and like discriminate anything, potentially you can do it. It's just maybe you'll need a complex model for that. Okay, so maybe any questions about the representation? Okay, so let's move to the invariance properties. Yes.
What's going to happen to all the parameters? Like, are you going to treat them as hyperparameters?
Oh yeah. So let's say there's no parameter. So we just fix a kernel at each layer.
Okay. So everything is fixed, like the weights of the Gaussian.
Yes. So these I will talk later about how they affect essentially the stability and invariance. Yes. So there will be some assumptions on like sizes of patches and pooling.
But eventually you're going to select them like it will be guided by theory. How you select them, or it will be gradient descent?
No. There's no gradient descent.
Okay,
yes.
Great.
Well, maybe some experience in the previous work of Julien have tuned something, but yeah. So you could just assume the simplest Gaussian kernel.
Do I have to worry about how as you're stacking up these layers, do I have to worry about, so each of these kernels you're constructing is going to have its own eigenspectrum, and do I have to worry about like how well they're aligned with each other, because otherwise I can like keep reducing the dimensions in which signal can pass through at every layer, like if they really
so you're talking about spectrum of the signal here, or of the...
Well, so the signal has its spectrum, and then each of these kernels that you're now combining is going to have, in particular, the part of its eigenspace that's sort of significant. So anyways, it's an RKHS, so we'll have some decay of eigenvalues, but just think about it, like the ones that are large. If they were really like very different from each other at each level, then effectively like these things will behave like they're orthogonal matrices, right? As they act on top of each other. So your information will, your signal will dissipate pretty quickly through these layers. So I guess what I'm sort of maybe not seeing so far, maybe you're going to talk about this at some point, is how to think about that. Like, do they end up being well aligned just by the choices you make, or?
I think, so you're asking like, how do we compare different kernels in terms of how they preserve sort of something?
Right.
So we don't want to like throw out information through the layers.
Right, or suppose for instance, I do want to make sure that, okay, if I will potentially lose some information. I'm okay with losing high frequency information in my signal, but I want to preserve as much of the low frequency information as possible.
So we have some things, some results about how like the final representation. So if the signal has not too many high frequencies, then sort of the norm. So there's some way to control sort of the norm in terms of how much it preserves the norm of the actual signal.
Right.
I'm not sure how much it makes. So actually in signal processing, people really care about this norm and they call it energy, and like they try to show that it's preserved. Here it's not clear that it's just as useful, but in practice, since you can discriminate a lot of stuff, then hopefully it means that they do preserve information. But yeah. Anyway, but later I'll talk a bit about more of the complexity aspects. Okay, so just invariant stability. So again, so we consider these diffeomorphisms here, C1, so smooth diffeomorphisms, and a deformation will be this L tau x here, where essentially you translate each point u by some different vector tau of u. So you can look at these pictures here to see what it looks like. So the point here is that it's a much richer group than just, so translation is just like a vector, so it's kind of if you're invariant to translation, it's kind of a weak thing, and you could achieve that with just sort of global pooling, which loses a lot of things. So here this can maybe tell you much more about how rich these representations will be. And so it's been studied for this wavelet-based transform here by Stéphane Mallat and Joan Brunel. And we try to extend it here to these kernels, so that potentially you can study how learning affects these things. Okay, so the definition is, as I showed before, there's like two terms. So typically you get, this is kind of the translation invariance term, and you want C2 to be small. And then the other one will be this deformation stability. So if you think of tau is something like zooming the image by a factor 1 plus epsilon, then essentially this will be epsilon. So you see that you're close as soon as you're not, as soon as epsilon is small. Okay, so just how do we show this? Just a warm-up is think about translation invariance. So because essentially all the operators here that we define are actually commute with these translation operators. I think, yeah, anyway, you can see it because so patch extraction is typically a bunch of translations stacked to each other by some amount in the patch. And then M is pointwise, is the nonlinear mapping. And A is just a convolution, which is covariant. So it's equivariant with translations. So yes, basically this is what we need. So every box here is like some operator. And when we have this property, you can just take this LC outside of the representation. And then you end up with this thing at the last layer, so some operator norm. And it turns out that you can bound this, so this has been studied similarly in the scattering transform. And so for some constant C, you get something that decays, it's like 1 over sigma n, which is the layer of, essentially the resolution at the very last layer. So if you did a lot of pooling, then at the end you have something that's quite invariant, basically as much as the last layer resolution. Make sense? Or?
It's just the property of the Gaussian convolution.
It's just pooling, I would say. So, but yes, it is intrinsic to how you do pooling. But even if you do average pooling, you would still have something similar. And in practice, people just downsample at each layer, or after every once in a while. And so at the end, if you have sort of a 4x4 map, this will kind of represent the entire image. So you will be invariant up to like the size of one pixel at the end. Sort of.
So this statement, this inequality, how general is it? Like this for what kind of AN? Like
so yeah, AN here, you need some kind of decay in the filter and some bandwidth. So here, this is specific to. I don't think it's specific to Gaussian, but it's specific to some kind of decay at the end of the filters. Okay, now how do we go beyond that? So the problem when you use deformation is that actually you don't preserve this the covariance aspect. So there's no commuting anymore. At least there is commuting with M because M is defined on each point separately, so that's fine. But for patches and pooling, then you don't really commute. So one thing we have is, so the pooling actually does commute, and in fact this has been studied before. So this AK, so you can rewrite it as just a commutator. This is actually controlled somehow by the amount of deformation. But these patch extractions are actually unstable. So yeah, I don't know the intuition is not necessarily easy to understand, but for instance, if you think of like a small rotation, then this could be seen as a small deformation. And if you first, and let's say the patch is just like 1 pixel, so there's just a tiny translation, then if you first rotate and then translate, it's different than like first translating and then rotating. And if you have some high frequencies in the signal, at some point there will be like some really things that are really close, but maybe very different values, and so this can explode, can kind of blow up. So the point is like, how do we control these two things together so that we can commute? We can kind of move this deformation operators up in the layers. And so what we do here is actually we assume that the signal originally has some pooling, and then every time we kind of control the two operators together. So because when you take some patches, you're typically taking them at some resolution, and as long as this patch is not too large, we show that you can actually control stability. So this is the condition that tells you the patch is not too big. So this is kind of like this diameter of the patch, and we say that it has to be controlled by the resolution at the previous layer. So this constant grows as beta to the. So d here is just the dimension of this signal, so 2 for images. So this is just beta cubed. And depending on the size of the patches, this tells you that small patches are better for stability. And there's some, yes.
They are in the RKHS, no?
Yes.
So shouldn't I take the norm of U? Or?
The norm of what? This?
Yeah.
So U here is just sort of the vectors inside this is the vectors inside a box. So it's just in R2.
But when I get further away, I mean...
This is a bound.
This is just like at
It's just the box. SK is the shape of the patch. So
okay.
We have all the
not
vectors.
At the case layer.
Yes, it's at the kth layer, but everything is defined always on L2 of this RD.
Oh, I see, okay.
So RD is kind of the same. Throughout layers, we have the same feature map. Yes. And okay, so this VGG, so a lot of networks nowadays actually use these small patches, so maybe it might be relevant for stability. And the final result, so if you stack this layer by layer, you get something like this. So we have what we had before, and then the stability part actually grows with the number of layers, but it also depends on this beta. And it turns out that if you want, so if your sigma n, the final level, let's say you fix the final level of translation invariance that you would like, then the number of layers will typically be logarithmic in something like sigma n divided by the original sigma 0, which is the frequencies of the first layer. So this tells you, so essentially we have that this n is logarithmic, whereas this one will actually grow as like beta cubed. So you want to sort of encourage a smaller beta, so smaller patches, and thus you will get maybe deeper networks, but more stable networks. And the other thing is, so there's another variable which is how much you want to pool, but if you pool too much, then we saw before that you will lose information because you will downsample too much. So this kind of like gives you some constraints and like nice architectures for stability, which is just keep growing things exponentially and do downsampling at the appropriate factors, and you will have something stable.
And C2 is just a universal constant, or?
C2, yes.
Okay.
Might depend on D, which is 2. But, yeah. Okay, so actually the same analysis applies also if you use something like CNN with some fixed weights and a ReLU, and you get a dependency on kind of the product of spectral norms here. But yeah, this is kind of a different point of view. Now you can extend this. I don't know how much time. Yeah.
Maybe a half hour.
Okay, so you can extend this to other groups. This is quite similar actually to other works that have been done in terms of like the equivariance that you can construct in your layers. So typically here everything was commuted with translations, but you can construct the layers so that they actually commute with richer groups, such as rotations or reflections or a mixture between rotations and translations. And typically what you want to do is have this equivariance, and at very end maybe you can globally pool over, let's say, a rotation component so that you're completely invariant to rotations. And this, we actually, okay, so you can define things appropriately. And for some examples, so for instance, this roto-translation group, which is, you can have both a translation and a rotation, then we show that by some appropriate construction, you can actually have both stability with respect to translations and some global invariance with respect to rotations. And you could probably, you could also replace rotations by something richer, like, I don't know, scalings, but you would need, the stability might depend on how the patches are affected by this rotation or whatever. So yes, but in fact, empirically, so here what we say is the pooling on the rotation group only has to be done at the end. And in fact, people have seen that if you do pooling at each layer, then you kind of lose. So the point of pooling at inner layers, as we show here, is that it's mostly about translation and stability with respect to translations. So you only need to do it on the translation group. But anyway. Okay, so now, yes, any
question? So if you have a neural network that outputs all zeros at the end, it's completely stable to all all deformations.
Yes.
So you do have to figure out how much information you're preserving from the signal, in addition to how stable you are.
Yeah.
So is there?
So this is kind of the, I mean, in our study, it's kind of the signal preservation aspect. So if you output, and there's also a norm aspect. So we also show that essentially the norm of phi for some signal is lower bounded by something about the signal original.
Yeah, but you're talking about the output at the end, how sensitive it is to the deformation at the input,
Yeah.
right? But you're not talking about whether the output at the end is useful for reconstructing the input, or how much information it still has. I didn't see that here.
So that's what he just said, that the norm of phi n x is lower bounded by something that depends on the norm of x. So that
So if you have
phi n
some
x
signal-
still has energy.
Finite itself is lower bound. Yes.
Yeah. And we show that, and potentially the kernel representation has, so the information thing is the signal preservation thing that we show. So potentially you can reconstruct sort of backwards in the layers. It doesn't necessarily tell you like if things are like nicely aligned across the layers, but it tells you that maybe the information is there for a network to learn.
Maybe the slide where you were talking about the deconvolution.
Yeah.
Maybe you want to explain that again.
Yeah, would that help? This one? Yeah, so this is kind of how we recover. So from some, okay, this is like the forward mapping. So we take patches and pooling, and then you do downsampling in a discrete case. And what we show here is that if you use some specific functions in the RKHS, you can actually recover this sort of the pooled version of the original signal. And then up to some deconvolution, you can get the original signal. So the deconvolution might be unstable, but
there's certain bounds there, right?
yeah.
Like you are losing some signal.
Yes.
On the other hand, over there, you're losing somewhat on deformations.
Okay.
So what is the trade-off?
Okay, so I mean, so the trade-off due to pooling essentially. So pooling will potentially give you some like instabilities in terms of recovery, but it will help you in terms of deformation. But if your signal is like very low frequency, then pooling will be fine. I mean, it won't like, it only affects the really high frequencies. So yes, there's some trade-off. A lot of people actually don't use pooling nowadays, but they're just hoping that maybe the network will adapt to whatever smoothness you require. But typically, the networks can still fit the training data, which means that you're not throwing away everything. So at least empirically, that might be a justification.
I guess maybe Nagoja was asking that if you think about like doing the trade-off quantitatively, then that can help you instantiate some of the choices in your architecture.
So, like how the scale of Gaussian pooling will affect. Yeah. So at least this thing is not really realistic, but it might be worth getting some bounds on the thing. Okay. I'll switch to. Okay, so now we'll talk about actually the RKHS sort of complexity and like what functions are inside the space. This is because this is what you actually can learn, and so maybe the norm of these functions will affect, will tell you how complex some different functions will be. So again, these are the kernels that we were considering, and then we can show that the RKHS in these small patch kernels, so if you only look at the kernel defined on a small patch Z here, then it will contain these types of functions. So if you remove this like homogenization thing, it looks kind of like a neural network. So just one unit neural network where G is maybe some weights. So potentially it's similar to what real neural networks learn. But here, so we do need some smooth type of activations. So here sigma has to have this like expansion, and essentially the norm will actually be controlled by the norm of G and how the expansions relate between the activation and the kernel. So this has kind of been studied before, and also a lot of people are using it nowadays. But we use essentially a homogeneous version of what has been studied before. And this is just to see that potentially these activations can look like a ReLU. So if it's smooth enough and you actually use this homogenization, then here for at least as soon as the weight is like not too close to zero, then the behavior is very similar to a ReLU. So this is what the smooth ReLU looks like, this sigma. And then if you do the homogenization here, the behavior will be sort of close to a ReLU. And these are just the complexities. So they're not they're sometimes exponential in the norm of the original, of the weight here. But this can still, at least it doesn't depend on like dimension and other things. So lambda here is like the norm of the vector. So here, g squared. So this is just some function of complexity, and that's just this lambda that we put here.
So are you sure for sigmoid, like lambda can be any constant, say larger than 10? Because I do recall, like for sigmoid, like the last equation holds maybe only for lambda being smaller than
one
constant.
Okay, smaller than?
Smaller than or equal to a constant, something like
yes,
that.
That might be true.
Yeah. Okay, just check.
Okay, and so now that we've defined these little units, you can construct like, so if you take a CNN with real weights, W here, these are like all the filters at different layers, layers K, and like you have different ones for each feature map. Then you can, you consider these activations that we have defined before, and then you can actually construct some CNN hierarchically and you can construct it hierarchically, and we can show that it's actually in the RKHS of the very final complete kernel. And then we can get some upper bounds on the norm. So the RKHS norm will be bounded in terms of essentially spectral norms at each layer of these matrices. And here, these are the complexity constants that you have. So yes, that question is a good one in terms of how far you can go in terms of the norms. And also here, they're not exactly spectral norms. They're like some mixed norms in terms of some L2 norm over the patch, over SK, and then of some spectral norm over the matrix. But so if you look at like linear layers, then you get essentially some product of spectral norm, which has been studied also for complexity of neural nets. Yes, so some links with the learning. So if we just consider the CNNs that are in the RKHS, then the RKHS norm is directly related to how hard it is to learn through Rademacher complexity. And so okay, so if you want to learn, maybe if you perfectly separate your data with some margin, then you get some generalization bounds in terms of this norm. And when you look at the spectral norm upper bounds, this is potentially related to other generalization bounds that it's not clear if they're actually relevant in practice, but they give you some measure of complexity. So finally, okay, so this is some more recent work on how we can actually leverage this complexity stuff to regularize in practice. Because, yeah, so the observation is that when we have small data sets, deep learning doesn't usually work very well. And also robustness properties. So we showed all the stability results for functions in the RKHS, but actually, neural nets are very unstable locally. So what's the deal there? So here, so the point is, can we regularize, using this norm potentially to, get better models for small data sets or for adversarial perturbations? So one way is just to use those upper bounds, so control the spectral norm somehow. But the other way is maybe you get some approximation from the lower bound side. And here, what we use is so here F is just some generic neural network. We just claim that even with a ReLU, maybe we're not too far from like something that's a smooth ReLU. And then we just use this variational characterization, and we can consider actually subsets of the unit ball to get lower bounds on this quantity. So one example here is if we take, okay, so maybe I didn't mention this, but the phi mapping is also non-expansive through deconstruction. So these vectors here, if you take u equals this difference, then when delta is bounded, is in a unit ball of like an L2 norm, then this will actually be in the unit ball of the RKHS, and so we get a lower bound on this norm through something like this. And then if you just use a reproducing property, you get essentially this lower bound that looks like some adversarial training type strategy. So in practice here, if you can do a few gradient steps near each image to like get some perturbation delta, then at some point you stop and then you take a backprop step with respect to F, and this will give you some lower bound, and you can control maybe the complexity of your function. You can do the same with deformation. So maybe if you have some MNIST digits, you can consider some like small transformations of them, translations or rotations, and then you take sort of the worst case one, and then you do backprop. And yeah, another one very related to this one is just a Lipschitz constant, so you can get essentially something in terms of gradients. This can also be computed in practice. It's called double backprop. And so it's just a gradient with respect to the input, and you take its norm.
Just a question. The bound of 1 on delta and the bound of 1 on u, these are not the same one, or are they?
So
like the fact that you look at the unit ball over u, and then you look at delta, which is bounded by 1. I mean, this depends on the stability of phi.
Yes, yes. We know that it's non-expansive. Phi.
Oh, phi is 1.
Yes.
It's 1 Lipschitz.
Yes.
Oh, yeah, that's right.
And because all the Lipschitz constant goes into F. So, but the first and the third are basically kind of the same set. But if your data is discrete, for instance, I'll show some results first. But so here, if you combine both some of these lower bounds, so these are just we added explicitly sort of as a regularizer, and we train with SGD. And then we can also control spectral norms through some constraints. And typically, if you use both, this will give like the best performance in a lot of data sets. So this is just a kind of a toy example on MNIST. If you, instead of like 60,000 examples, you take 300 or 1,000, then these are like combined methods where we use maybe those two lower bounds on deformation and perturbations. The star means that you actually include data augmentation. But even, so here maybe the simplest, so even if you consider these two, so just the sum of like, this is additive perturbations and transformations, then you get something like 95, whereas if you only do weight decay, even if you include data augmentation, you get to like 92% accuracy. So just using this explicit regularizer can do better than just data augmentation. And then,
what is the experiment here again? Sorry.
Okay, so we take 300 data points from MNIST, just fixed, and then we look at test performance on MNIST, but we regularize during training using different strategies. So this is not robustness, it's just small data, and you want to generalize well.
I fix my, like, the neural network is fixed as a kernel. Is that what I'm doing?
So, okay, the point of view here is that F, when you train a neural net with ReLU, you can view it sort of in the RKHS and leverage the knowledge of the norm to regularize it. Even though we're not using a kernel method, so it's just an empirical regularizer.
But am I only training the last layer?
No, everything.
Oh, you're training everything from 0. Oh.
Yes, we use the like standard initialization. It's just that we encourage essentially the inductive bias of our kernel by regularizing explicitly.
You get these results with 300 examples.
I mean, MNIST is very easy. You can typically get 99% very easily.
With 300 examples?
No, not with 300 examples. But this is not that good for MNIST. But
I find it good with 300 examples.
So just to make sure, 30 per class, right? So 300 is
it's pretty small. Yeah.
Not just making sure 300 is not per class.
No, yes, total.
Okay.
But so you have all the classes, 10 classes.
Yeah.
Are there other methods that can do that?
So actually, I did try. So on this specific example, I did try just the CKM thing approximation, and it kind of works almost as good as like the final things. So if you use the actual kernel with some kernel approximations, just 2 layers. So this is I think 5 layers, the network that we used, and we use backprop. Whereas if you use the actual kernel with 2 layers and you approximate it using some nice things, then you get, and you regularize explicitly just the last layer, then you get something like 95 on this 300 thing. At least this is like preliminary experiment. I thought about putting it here, but then I figured that maybe I shouldn't because it might affect the reviewers. But and so here, then when you kind of combine everything, you typically get sort of the best performance here. And the other one that's maybe less of a toy problem is there's these. So in biology, it's quite common actually to have small data sets. So here you have like 100 data sets with each one 100 like protein sequences, and here we use like a 3-layer like convnet on 1D, so here actually these perturbation-based penalties work pretty well. And the other thing is, in this data set, the data is actually discrete. So if you use the gradients, it's not clear that you will control everything. But with these adversarial perturbations, you're somehow controlling things outside of this discrete input set. And this is some kind of, so we have like 50 data sets for training, and we use fixed hyperparameters for all the data sets. And here you get something like, this is some kind of AUC average AU ROC 50. for these biology data sets, and it seems to help quite a lot in these tasks. So I think the state of the art is in the ballpark. They might be using some also deep nets, but like different kinds of architectures. But and finally, something on robustness. So there are links between this explicit regularization and like just adversarial training, where you use the robust objective. In fact, you can, if L is like 1 Lipschitz, then typically you get a lower bound by optimizing the robust loss, which is on the left here. So people often use this for robustness, and here we kind of advocate for potentially using this directly, because when you have a neural net, this might actually just completely fit your data up to the perturbations, whereas here we have some more global control of robustness. And so also when you control complexity, if we actually knew this norm, then you can show some like margin bounds, adversarial margin bound type things. But in practice, we do see a little bit of loss. If you regularize, we might lose some performance, at least on these full CFAR data sets. So this is just a picture, but okay, this is like for a larger budget of adversarial, if the adversary is like 1.0, then this is like PGD, which is what people often use in practice. So here you have standard accuracy and sort of adversarial accuracy with this attack. So here, as you increase regularization, you will increase robustness, but you might lose some accuracy. And for our methods, which is sort of this yellow one or these gray and purple ones, then you are a little bit under, so you do lose some accuracy for like small regularization. But at the very top here, it seems like we do gain in terms of robustness compared to this PGD type methods. Yes, with data augmentation.
Because actually, I tried this idea last year and it didn't work, but it was for L infinity robustness.
Okay, so you had like a separate regularizer?
Like the Lipschitzness, the grid.
Yeah, okay. Yeah, for L infinity, so this is all L2?
I never tried L2.
Okay, maybe it's only for L2 there, I don't know. But L infinity is a bit weird for neural nets, just because everything is Euclid. I mean, maybe L2 is more natural, but yeah. But at least here we're controlling sort of the full smoothness of the functions, and maybe, yeah. But yeah, I'm curious about maybe trying that out. Okay, this is just, so actually this PGD, when you regularize more and more, it turns out that empirically we see that the norms just kind of grow and explode, where this is the product of spectral norms, whereas the other methods that we use, they actually control these very well. So maybe there's less overfitting, you're actually controlling smoothness, whereas robust optimization might just like overfit, even though it turns out that it works well on these image data sets. Okay, so just to finish, just a recap, we have these nice stability properties. We can show some signal preservation properties, and then we can extend translation invariance to other groups. Then we see how you can control complexity of models in different ways. You can also explicitly regularize using the insights of our theory. And finally, okay, one word about the NTK thing. So if you've heard of it, basically there's some regime in which like super overparameterized network actually stay very close to initialization and basically behave like a kernel method. And the kernels that arise in this regime are kind of similar to ours, even though they have like multiple terms. But we have some basic results so the stability actually is preserved, even though it's a bit weaker. So sort of instead of being like Lipschitz, you're maybe like Hilbert smooth, you're a bit less smooth, sort of like with a square root. But in contrast, you get maybe some better approximation properties. So if you look at the kernel, at least for one layer and ReLUs, you get sort of a slower decay of eigenvalues in the kernel, which can essentially lead you to, with a fixed norm, you can approximate like a larger class of functions. So potentially, if you have a lot of data, it can be helpful. It can be a better kernel than like the kernels that we consider here, but essentially the properties are quite similar. So I'll stop here.
Time for some more questions.
Yeah.
So yes, everything you talked about for the most part was in some ways in sort of mostly in the I guess representational setting, a little bit about the sort of finite sample or generalization setting when you're thinking about the model complexity. But sort of obviously the missing ingredient is the optimization aspect, because I think like From most worst case perspectives, we don't fully think that neural networks would behave as well as they do if we take away the specific ways we optimize them.
Yes.
So how does that sort of interface with anything that you've been thinking about?
Yeah.
Where would you inject the optimization properties?
Yeah, I mean, so this last one is kind of like a nice link, although it's not clear if it's like the right regime. And in fact, it probably isn't. But so I think, at least if you're studying these kind of signal processing type properties, it makes sense to have a nice representation to study. So here we're just, whatever, we don't care about the weights, we just look at like the architecture, what does that buy you in terms of inductive bias. But it's true that in practice, really the optimization will determine a lot of stuff.
I guess I was particularly curious because you're kind of talking about explicit regularization, and we know that optimization does inject inductive bias as well.
Yes.
If the problem is simple enough, we know for like it really corresponds to a minimum norm type bias.
Right. Okay. But minimum norm.
So
sometimes minimum norm is not. So even if we were in that setting, and even if the actual norm that was controlled was like a kernel thing,
right.
Then in some problems it still helps to actually regularize. So that was kind of the regularization aspect. And in fact, if you use the full training set, then just regularizing for the sake of doing it will typically reduce accuracy, like generalization. But yes, I think, I mean, I don't think we understand enough like the optimization aspects. So this one is like probably the easy, I mean, NTK is like an easy way to study these properties, but in terms of actually learning structures and stuff, that would be an interesting question. Like maybe potentially when we actually, so we do enforce pooling, and ideally people don't always use pooling, so maybe if you could actually learn something that it's smooth, and maybe gradient descent automatically learns it, then you could get better stability. But,
Okay, thanks again.
Okay. Thanks.